So I want to now go through fluid dynamics or moving fluids now that we've discussed static fluids. And before we get into any of the actual content, I want to first point out that anything we discuss in this section, I will be assuming it's an ideal fluid, meaning it's not compressible. Even if I happen to talk about a gas, I'm going to make the assumption that it's non-compressible for the purposes of this. And you guys already have a rough idea. If you put your thumb over the end of a hose, why does it get faster? You guys have all played that where you shoot your siblings with your thumb over half of the hose. But why does it get faster? And that plays into fluid dynamics. That's a very big part of it. And I'm hoping that you can see in this diagram that really we're looking at the hose in reverse. When you put your thumb over the tip, you make a smaller entrance or a smaller exit. So the water coming in from this side is going to get funneled down into here, and it gets in a smaller area, and smaller area would mean higher velocity. That's the crux of this part of it. So smaller area, higher velocity. So when you put your thumb over it, you make the hose have a smaller cross-sectional area, which would mean a higher velocity. And that brings me up to my next point, is whenever you're talking about the area of a pipe, you need to consider whether it's a rectangular pipe or whether it's a round pipe. If it's a rectangular pipe, well then the cross-sectional area would be length times width. But with a round pipe, as we have over here, your cross-sectional area would be a circle, in which case you would need to know that the area equals pi r squared. That it will be assumed that you can make those leaps moving forward. So now if we look at it in the direction that the arrows are moving, and you could do this in reverse too, but I'm going to go with the arrows for this one. Because the mass or the amount of atoms flowing through one section of the pipe won't become less or more because they have to push the atoms in front of them. So you have a bunch of cross sections, each pushing the cross section in front of them. As those cross sections get to this area, because the pipe changes shape, gets bigger, gets smaller, whatever the case may be, the amount of total water flowing at any single cross section doesn't change. So the cross-sectional flow rate, or rather volume flow rate, remains constant no matter where in the pipe you are. So this equation right here will calculate the volume flow rate. And it is equal at all points because each cross-sectional area, each volume flow rate, needs to push the cross-sectional area ahead of it. So your volume flow rate at location 1, A1V1, is going to equal your cross-sectional area at, or your, volume flow rate at section 2. And again, to calculate your volume flow rate at any point, it's the area at that point times the velocity of the fluid at that point. So we take this cross-sectional area, or pi times radius 1 squared, A1, and multiply it by the velocity at whatever that location is. So along this, as we go to from section 1 to section 2, what happens to the area? Well, we start with a small area, and we go to a big area, because this is a small circle, and this is a big circle. So the area gets bigger, but if this whole side has to equal this whole side, what would have to happen to the velocity? So we're going to mathematically justify that. If this total product equals this total product, then a small area would have to be multiplied by a big velocity to compensate for the big area, which is going to have a smaller velocity. That makes sense. Smaller area, higher velocity. Think of the hose. That's the big takeaway I want you guys to get from this. Faster area, larger area, slower velocity. Smaller area, faster velocity. And this equation will be useful because there will be a situation where I give you this area and this velocity, and then hopefully you can calculate the velocity at location 2. And we will work through one of those problems in a couple of slides. But what is the cross-sectional area of a pipe and how is it calculated? I kind of got ahead of myself. The cross-sectional area of a pipe is a circle. And, circle. And the way we calculate it is pi r squared. Circles, yo. So Posty says, he gives you a very important thing, be careful of diameters. I'm pretty sure he said that at some point somewhere. So when you're working with this, a lot of times they'll tell you a pipe has a diameter equal to 2 centimeters. So if diameter equals 2 centimeters, you're going to have to first get it into a radius. And to go from diameter to radius, and again, diameter is the whole height of the pipe, the radius would be half of that, or 1 centimeter. And as we've done every time, your units can't be in centimeters. You need to convert them to meters. So to get from 1 centimeter to meters, how many cents are in a dollar? 100. So we divide it by 100 to go from centimeters to meters, and you end up with a radius equal to 0.01 meters. Thanks, Post. So now let's try an example problem. We have a circular pipe of non-uniform diameter. That just means the diameter changes as we go from point 1 to point 2. At one point in the pipe, the radius is 2 centimeters and the flow speed is 6 meters per second. A, what is the volume flow rate? And again, we go back to that volume flow rate equation, which is area times velocity. Now, I've already gotten ahead of myself. Whenever I look at a problem, the first thing I want to do is look at a diagram. So they say it's a non-uniform diameter, so I'm just going to guess that the diameter gets bigger. And we know that at one point in the pipe, I'm just going to call it this cross-sectional area. The radius is 2 centimeters, and the flow speed, the velocity, is 6 meters per second. Again, we can't be in centimeters, so to get from centimeters to meters, we have to divide by 100. So instead of 2 centimeters, we're going to have a radius equal to 0.02 meters. And I'm actually going to erase this so that I have enough room to work through this problem with you guys. So I'm going to move that note over there. So now we can do part A. We can calculate the flow rate. And remember, this is area, not radius. So you need to plug in pi r squared and then multiply that by the volume, the flow speed, times velocity. So pi times 0.02 squared, and I should include my units, meters, 0.02 meters squared, times pi, times the velocity of 6 meters per second. And when I plug that into my calculator, and I'm just going to use 3.14 because it's close enough. It's a close enough approximation of pi, but you could leave your answer in terms of pi. And I'll do it both ways so you can see. 3.14 times 0.02 squared times 6. And we get 7.54 times 10 to the negative 2 meters squared times meters per second, or cubic meters per second. And that unit makes sense for a volume flow rate. This many cubic meters of water are flowing through the pipe every single second. So that's our flow rate, and I'm also going to calculate it but leave my answer in terms of pi. So I'm going to keep pi as a unit, or rather a multiplier, and just not include it in my math. So instead of multiplying by pi, I'm just going to do 0.02 squared times the velocity of 6 and get 2.4 times 10 to the negative 3 times pi cubic meters per second. Both of those answers are equally valid. I am okay with either of them, and they are both acceptable. Now B, what is the flow speed at a point where the pipe constricts down to 1 centimeter? Okay, so this is where that volume flow rate equation comes into play. We know the volume flow rate at any point in a pipe has to equal the volume flow rate at any other point in a pipe. So we've gone from 2 centimeters and we're going down to 1 centimeter. So actually my initial guess that the pipe got larger was incorrect. So I'm going to go and redraw my diagram. And we've gone from a radius of 2 centimeters or 0.02 meters. And now we're going to an area where the radius equals 0.01 meters. And now we're going to use the continuity of flow rate equation, or rather, area 1 velocity 1 equals area 2 velocity 2. This is a critical equation, but it is on your equation sheet, so you do not have to memorize it, but you do need to be able to use it. Well, we've already calculated A1 V1, and I'm going to go ahead and use my first answer, 7.54 times 10 to the negative 2 cubic meters per second, and set that equal to A2 V2. Well, we're trying to calculate the flow speed or velocity. So that's ultimately what I'm trying to calculate is V2. Did I choose the right color? I think I did. So now we're going to calculate A2. Nope, that's the wrong color. And plug in our area 2, which is pi times radius 2, 0.01 meters. Don't forget to square it, times velocity 2. And now it just comes down to algebra. Ooh, I'm sorry, I put in v squared. That should be velocity 2. So now we're going to divide both sides by pi to cancel this out. And we're also going to divide both sides by 0.01 meters. Don't forget to square it so we can cancel this out. And plugging that into a calculator to save myself time and effort, 7.54 times 10 to the negative 3 divided by pi divided by 0.01 squared. And that should give you 24 meters per second. So 24 meters per second should be our second velocity. And that compares to the initial speed of 6 meters per second. And that, anytime you get to an answer, you should think to yourself, does this answer make sense? Well, the pipe got smaller, which means the velocity should get faster. So yes, our velocity went from 6 meters per second to 24. That makes sense. And the other thing is, to get from 6 meters per second to 24 meters per second, it got quadrupled. And it got quadrupled because the area, or rather the radius, got cut in half. And if the radius got cut in half, the area, because radius is squared, is going to get cut in 1/4. So going back to that continuity equation, A1 V1 equals A2 V2, if the area gets cut in 1/4, to compensate for it, the velocity is going to have to be multiplied by 4. You don't have to have that cold. We will discuss how to determine relationships later, but I wanted to point it out while we had this really good example problem. All right, so that's the first part of fluid dynamics. So now let's get into part 2, and we're going to go back a little bit and discuss conservation of energy and then apply it to this. So you guys have heard energy can never be created or destroyed. It can only be converted from one form to another. So the two main types of energy we've always discussed are potential energy and kinetic energy, where potential energy is stored energy. And usually in physics class, we're talking about due to height, and kinetic energy is moving energy. So if we look at this example problem, this person is at the top of a roller coaster, and he's not moving at the top, so he has 0 kinetic energy. but he has a lot of height, so that means he has a lot of potential energy. So he has 100 joules of potential energy and 0 joules of kinetic energy. The key takeaway I need you guys to have is his total energy is 100 joules, and that total is just the kinetic plus potential. Now, when he gets to the bottom, he no longer has any height, which means he no longer has any potential energy. And energy can't be created or destroyed, so that energy has to go somewhere, and in this case, it got converted into moving energy, kinetic energy. But we still have 100 joules total. And that's true anywhere we look. 50 and 50 is going to be 100. 75 and 25 is going to be 100 joules of total energy. So the kinetic plus potential equals the total energy. And I'm going to actually give you guys a little bit more of this equation, or go through it a little bit more in depth. So the total energy, or mechanical energy at position 1, and I'm going to call this position 1 and this position 2. The total energy at position 1 equals the total energy, or mechanical energy, at position 2. So the potential at 1 plus the kinetic at 1 equals the potential at 2 plus the kinetic at 2. Ooh, I'm sorry, I'm going to change this. I'm going to ignore this location, and I'm going to call this position 2 at the bottom, because I think that helps. So with that, the kinetic and potential at 1 equals the kinetic plus potential at 2. Now, we haven't gone over this year, but the equation for kinetic energy is 1/2 times mass times velocity squared. You don't have to know that, but it will make the next, how we apply this to pressure, make a little bit more sense. So for now, suffice it to say that 1/2 mv squared is kinetic energy. And just kind of look at that equation and think about it for a second. More mass, more energy. More velocity, more kinetic energy. Potential energy is calculated relatively similarly. It is mass times gravity times height. More mass, more gravity, and more height all mean more gravitational potential energy. So taking these two equations and plugging them in to this step would tell me, well, mass times gravity times height 1, the potential energy at 1, plus 1/2 mv1 squared, or kinetic energy at 1, equals potential energy at 2 plus kinetic energy at 2. mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared. Total energy 1 equals total energy at 2. You do not have to know this, but it parallels Bernoulli's equation for how this applies to pressure. So instead of energy being conserved, we're going to look at how pressure is conserved through energy. So we're going to add the height energy and the moving energy of fluids and set those two equal to each other. Except it's not going to be energy, it's going to be pressure. Now look at this equation, 1/2 rho v squared. That's the kinetic energy per volume. That equation, that equation completely parallels 1/2 mv squared. So that's your kinetic energy portion of this equation. And again, you don't have to know that, but it has value to recognize where this is coming from. Similarly, rho gy parallels mgh. So instead of mass, we're just plugging in density, rho. 1/2 mv squared, 1/2 rho v squared. mgh, rho gh. And instead of y, for the most part, we will be using height. So even though this equation has y in there, we are going to be using rho gh, but it doesn't matter. Now, a couple things to note. Over here, I have the variables listed. P is the pressure. So at any point in a pipe, you can calculate the total pressure in the pipe as the pressure inside the pipe plus the kinetic pressure in the pipe, 1/2 rho v squared, plus the potential pressure in the pipe, rho g y. And that will give you the total pressure in the pipe at that point, where P is the initial pressure, rho is the density of the fluid, V is the velocity of the fluid at that location, G is gravity, 10 meters per second, and H is the height above the ground. So right now this is at what I would call height equals 0, which would mean this last term, density times gravity times a height of 0, is going to give you 0. So you are going to have to choose a reference height, and I will show you guys how to do that. So the sum of the pressure, the kinetic energy, and the potential energy all have the same value at all points along the streamline. So instead of energy being conserved, 100 equals 100, the total pressure will be conserved from point to point. So instead of kinetic energy turning to potential energy, moving pressure is going to turn into gravitational stored pressure or potential pressure. Now, it's conserved from point to point, meaning the total pressure here is going to have to equal the total pressure here. And this equation is the total pressure. So the total pressure, initial pressure plus kinetic pressure plus potential pressure, is going to equal initial pressure plus potential pressure plus kinetic pressure plus potential pressure at point 2. So we have position 1 and position 2. So the total pressure at one place equals the total pressure at the second place. This equation is long and it is involved. It is the longest equation you will have all year, but it's on your equation sheet, so you do not have to memorize it. You only need to know what the variables represent and be able to apply it. Now here's that same equation more simply. Total pressure equals total pressure. And that's at point 1 and that's at point 2. So you can pick any two locations at a pipe and apply this equation. In fact, you could have chosen a third location, which I'm going to call location 3, and say, okay, pressure 3 plus potential at 3 plus kinetic at 3, rho v squared 3. All three of those points are equal to each other. You could do that for an infinite number of cross-sectional areas. Total pressure remains constant. That's the big takeaway. And one last thing that I do want to point out is in this equation, the pressure, if open, and I have this in the notes later, but I'm going to say it now because it's relevant now. If it's open to air, this P, the pressure, is equal to atmospheric pressure. Or in pascals, that would be equal to 100,000 pascals, or 100,000 newtons per meter. So now let's actually apply this equation a little bit. We have a larger pipe traveling to a smaller pipe. And my first question for you is, what's going to happen to the velocity? Well, as the area gets smaller, the velocity should get faster. Thumb over the hose. We know the velocity at the bottom of the pipe is 2 meters per second. And we know the velocity at the top of the pipe is 3 meters per second. We also know that position, I'm going to call this 2 and position 1. Position 2 is 10 meters higher than position 1. Whenever you get a problem like this, you have to choose a base height or a reference level. I'm always going to assume that the bottommost position or this location is where I'm going to say height equals 0. That will save you a lot of effort with your problem. So I'm going to say height equals 0 at the very bottom, which would mean at position 2, height would be equal to 10 meters. So now we need to figure out what's the pressure in the top gauge. This is where we're going to use Bernoulli's equation. Pressure 1 plus potential at 1 plus kinetic at 1 equals pressure 2 plus potential at 2 plus kinetic at 2. And we know the density of the fluid should remain constant. In fact, this one is water. I cut that part out, but we're going to say that this is water. So pressure at 1, okay. So pressure at 1, this is a gauge pressure of 200 kilopascals. And a reminder that kilo means 1,000. So 200 times 1,000 pascals is the gauge pressure. But keep in mind, the gauge pressure is always 100,000 pascals less than the real pressure. So instead of this just being 200,000 pascals, because it's a gauge, we have to remember to add that extra 100,000 pascals. And that's something that the more you do, the more you'll remember to do it. So the pressure at 1 equals 300,000 pascals plus rho, and the density is 1,000 because it's water. Gravity is 10. And the height at 1, we chose our height at 1 to be height equals 0, which means 1,000 times 10 times 0 is going to give us 0. But now we need the kinetic at position 1, 1/2 rho v squared. We know the density is 1,000. And they gave us the velocity of 2 meters per second? 2 meters per second. 2 meters per second. Don't forget that gets squared. And set it equal to the Bernoulli's total pressure on the right side, or at position 2. So pressure 2, that's what we're trying to solve for. So I'm actually going to highlight that so I don't forget. So pressure 2, what we're trying to solve for, plus the potential at 2, 1,000 times 10 times the height at position 2. Well, if this is height 0, that would make this 10 meters high. Plus the kinetic at 2. 1/2 times 1,000 density times the velocity, 3 meters per second, but don't forget to square that. So now it's just algebra solving for P2. This is the only unknown variable, which means we can very simply solve for it. So now, with a little bit of math, 300,000 pascals plus 1/2 times 1,000 times 4 would be 2,000 pascals. Did I math that right? 4 times 0.5 times 1,000. 2,000 pascals. I'm sorry, I'm going to be extra careful because I would hate to do this whole thing with a simple math error in it. And that's equal to pressure 2, and again, that's what we're trying to solve for. Plus 1,000 times 10 times 10, or 100,000. And again, you can't compare, not again, I haven't said this yet. You can't add apples and oranges. So if any one of these is measured in pascals, then all of the other ones are also going to be measured in pascals. If you guys want me to work through the derivation of how rho GH equates a pascal, or 1/2 rho v squared equals a pascal, ask me and I'll work you through it. But 1,000 times 10 times 10 is going to give us 100,000 pascals. And 1/2 times 1,000 times 9, 3 squared. 9 divided by 2 times 1,000 should equal 4,500 pascals. I'm going to combine these two, and P2 plus 104,500 pascals equals, combining these two, 302,000 pascals. Now, again, we're trying to solve for P2. So I'm going to bring this 104,500 to the left side. I'm going to subtract it from both sides. So 302,000 minus 104,500 should give us 197,500 pascals equals the total pressure at 2. Or rather, the pressure on the fluid at 2. But they didn't ask for the pressure at 2. Always go back and reread the question before you are necessarily done with your problem. They wanted to know what the pressure gauge read. All right, so because a gauge always reads 1 atmosphere or less, it starts at 0 pascals. To find the gauge pressure, it's the pressure of the fluid minus the atmospheric pressure. So that would be 197,500 pascals minus the 100,000 pascals of atmospheric pressure. And that should leave you with the gauge reading of 97,500 pascals. So that's the gauge pressure at location 2. I know that's a bulky problem. If you need to, go back and try to work through it on your own. There's a lot of value in that problem. All right, so before I end this, I have one final thought and derivation. You do not need to know how to do this derivation, but you need to know the result. So if you want, you can skip through and get to my big takeaway. But how do velocity and in turn area relate to pressure? Some of you guys probably remember the answer from 9th grade. Higher velocity would mean blank pressure. Higher pressure or low pressure? I don't know. Well, I do know, but we're going to work through it together. And we can use Bernoulli's equation to figure that out. Pressure 1 plus rho GH at position 1 plus 1/2 rho V squared at position 1 equals the same at position 2. Now, we know because the height doesn't change, then we can call this height equals 0, which would mean this would collapse to 0 and this would collapse to 0. Again, whenever you guys start these problems, you're going to have to choose your own reference height, your own place where you say height is equal to 0. I always choose the lowest position. You choose for yourself. But those both collapse to 0, and now we're left with the pressure at 1 plus 1/2 rho V squared at 1 equals pressure 2 plus 1/2 rho V squared at 2. Whew. Well, the density of the fluid doesn't change, so we can't cancel it out, but that means it's not going to affect anything. But if we say the velocity at 1 is x, as we go from position 1 to position 2, you should be able to accurately predict what's going to happen to the velocity. Because the pipe gets smaller, the velocity should get higher, which would mean this entire term is going to get bigger. And if pressure 1 plus x equals pressure 2 plus a bigger value, if this is bigger, then this is going to have to be smaller to compensate for it. So a bigger velocity, a bigger kinetic pressure, would mean a lower pressure on the fluid, a lower pressure in the pipe. So high velocity means low pressure, which should make that lesson from 9th grade finally all come together as one. So high velocity, low pressure. That's your big takeaway. And similarly, high velocity, low pressure, and vice versa. Low velocity, high pressure. And with this, you can also make the extrapolation more area you know is going to mean less velocity. and less velocity means more pressure. So a larger pipe is going to have more pressure. A smaller pipe is going to have less pressure. And that works as a general rule. Thank you guys for sticking with me through this. I hope that for the most part makes sense before we start working on some practice problems. If you have any questions, please feel free to let me know. And I hope you guys have a great day. Thanks a lot. Bye.